In this video, we're going to look at arc length and sector area. In particular, we're going to use central angles in a circle and the radius of the circle to find the length of a subtended arc and the area of a sector of that circle.
Let's start by considering a circle with a radius of length r and a central angle theta that's measured in radians. Given this situation, there are two geometric objects which are related to angle theta. The first is the length of the arc of our circle, which is being subtended by our angle. In other words, the arc between the endpoints of our angle. We'll call the length of that arc the arc length and denote that by the letter S. So S here will stand for the length of that particular arc, which will depend on the angle theta, as well as the radius of the circle. The other geometric item here that is related to theta is the area of the sector that is swept out by theta. And so here we have a sector area, which we can denote by a capital A. Both of these quantities are determined by the angle theta, measured in radians, as well as the radius of our circle. And so for this video, we're going to look at how to determine these two quantities based on our angle and our radius of our circle. The key to deriving formulas for the arc length and sector area is that the central angle in that picture is theta over 2 pi of a full rotation. That fraction theta over 2 pi can be seen by realizing that the central angle is theta radians and the full rotation is 2 pi radians. And so taking theta divided by 2 pi will give us the fraction of a full rotation of that central angle. In particular, this tells us that the arc length S is going to be the same fraction, theta over 2 pi, of the circumference of the circle. And we know that theta over 2 pi of something means multiplication, and the circumference we know is 2 pi times the radius r. And so here we have the 2's will cancel and the pi's will cancel, and we're left with theta times r. And so we get the traditional arc length formula that the arc length S is equal to theta, the central angle, times the radius r, with the caveat that theta is in radians. This is an important observation that theta must be in radians for this formula to hold. If we're given a central angle in degrees, the first step must be to convert that central angle to radians and then apply this formula. In this example, we want to find the arc length along a circle that has a radius of 7 feet and subtends a 300-degree angle. Since our angle is given in degrees, our first step is to convert that to radians. So theta here would be 300 degrees. In radians, this would be 300 times pi over 180. And when we simplify this, this becomes 5 pi over 3. So this central angle is 5 pi over 3 radians. Once we know the angle in radians and we have the radius of our circle, the arc length formula simply tells us that the arc length is theta times r, which is 5 pi over 3 multiplied by 7, or 35 pi over 3. And this will be in feet because the radius of our circle was given in feet. So the length of our arc, or our arc length along the circle on this particular angle is 35 pi over 3 feet. If we used 300 in this formula, notice that we would have ended up with 2,100 feet. And this is very different. 35 pi over 3 is going to be roughly a little bit more than 30 feet if we computed the exact or an approximate value of that. So a very different value than we would have obtained if we used our angle in degrees. So this is the most important thing about this formula, is to remember that the angle must be in radians when this formula is used. To find a formula for the area of a sector, we again go back to our key observation that the central angle in our circle is theta over 2 pi of a full rotation. Using similar logic that we used for arc length, that means that the sector area is going to be theta over 2 pi of the entire area of the circle. And so taking a fraction of some quantity is multiplication. And so we have theta over 2 pi of the area for a circle of radius r, which is known to be pi r squared. Here we have pi's canceling out, and nothing else will simplify here. And so we have theta over 2 times r squared, which is sometimes written as 1/2 theta r squared. And again, theta will be in radians. And this is our formula for the area of a sector with a central angle of theta radians and a radius of r. In this example, we want to find the area of a sector subtended by an angle of 105 degrees in a circle of radius 10 centimeters. Again, we're given an angle in degrees, and so our first step before using the formula is to convert this degree measure to radians. As usual, we'll multiply 105 by pi over 180, and this will simplify as 7 pi over 12. So this particular angle, the central angle here in this example, will be measured as 7 pi over 12 when measured in radians. To compute the area of that sector, we use our formula 1/2 times our angle, 7 pi over 12, multiplied by the radius squared, so 10 squared. Here we can do several steps to simplify this. Of course, this is 1/2 times 7 pi over 12 times 100. The 1/2 times 100, of course, will be 50. And finally, we can simplify the 50 and 12 and get 175 pi all over 6. And here, since we're computing an area, this will be a squared units, and our radius is in centimeters, and so we end up with 175 pi all over 6 centimeters cubed, or centimeters squared. If you'd like some extra practice with these concepts, you could try these two examples. First, find the length of the arc subtending a 225-degree angle in a circle of radius 10 inches. Then find the area of a sector of a circle with radius 4 yards subtending an angle of 150 degrees. The answers to these questions will appear in just a few seconds.